The observable universe stretches 46 billion light-years in every direction. But what if you tried to go there? If you built the fastest spacecraft imaginable and traveled non-stop, would you ever reach the edge? Or is the boundary of the universe something you can see but never touch? What observable universe actually means? The universe is vast, but when we try to measure just how vast, we quickly realize that words begin to fail us. We like to think in kilometers, miles, even light years when talking about space, but none of these units really capture the enormity of what surrounds us. Today, if we were to try to reach the farthest regions of the cosmos, we would confront a staggering, almost incomprehensible distance. The edge of the observable universe, stretching out over 93 billion light-years in diameter. To put that in perspective, a single light-year, the distance light travels in 1 year, is almost 6 trillion miles. And yet that unit, colossal as it is, barely scratches the surface when we attempt to map the total distance to the outermost reaches of what we can see. When we speak of the radius of this observable universe, it is around 46.5 billion light-years. And here is the shock that grips the imagination of anyone who has ever looked up at the night sky. Even if you could travel at the speed of light, the fastest speed known to physics, you could never, not in your lifetime, reach this cosmic boundary. The universe is expanding as you travel, carrying the farthest galaxies away faster than you can catch them. Light itself, racing across the cosmos for billions of years, is still just a fraction of the way to the true edge. This is not speculation or imagination. It is a reality written into the very fabric of space and time. But what does this edge really mean? When scientists talk about the edge of the observable universe, they are not referring to a physical boundary, a wall, or a rim beyond which nothing exists. Instead, it is the limit defined by the light horizon, also known as the cosmic light horizon, the maximum distance from which light has had time to reach us since the beginning of the universe, roughly 13.8 billion years ago. The observable universe is a sphere around us, defined purely by the distance light has traveled in all directions since the Big Bang. Beyond that sphere, there may be galaxies, clusters, even entire universes. But their light has not yet reached us, and so they remain invisible, tantalizingly out of reach. This horizon is determined by the finite age of the universe. Time, like space, has a beginning, and so does the light that fills the cosmos. Every photon that strikes our telescopes today has traveled for billions of years, carrying the imprint of cosmic history, but only so far. The universe may be infinite, but our observation of it is necessarily limited by time itself. Before the 20th century, the stars and galaxies we see were often believed to be confined to a single Milky Way-sized island of light. The notion that our galaxy was just one among billions, expanding away from all others, was revolutionary. The first clues to this startling reality came from the careful measurements of light emitted by distant galaxies, a light that held a hidden message in its wavelength. In 1929, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that would forever alter our understanding of the cosmos. Hubble measured the light from galaxies at varying distances and noticed something peculiar. The spectral lines, the fingerprints of elements like hydrogen and calcium, were shifted toward the red end of the spectrum. This redshift indicated that these galaxies were moving away from us. Even more astonishing, the farther away a galaxy was, the faster it appeared to recede. This observation, now famously encapsulated in what we call Hubble's law, demonstrated that the universe was not static, as had long been assumed, but expanding. The distance to a galaxy multiplied by a constant, the Hubble constant, gave its recession velocity, revealing a cosmos in motion, a universe stretching outward in all directions. This discovery was not made in isolation. Nearly 2 years before Hubble's announcement, a Belgian priest and physicist named Georges Lemaitre had independently reached a similar conclusion, deriving mathematically that the universe must be expanding, a result that he presented in 1927. Lemaitre's work suggested that the universe had once been far smaller, denser and hotter, implying a beginning in time, a cosmic genesis that would later be called the Big Bang. Hubble's observational confirmation gave Lemaitre's theoretical predictions the empirical weight they needed, merging observation with theory to create the foundation for modern cosmology. It was an era in which the sky, long thought to be eternal and unchanging, revealed itself to be dynamic, vast, and ever-evolving. Every measurement, every spectrum, was a window into the history of a universe in motion, an enormous stage on which galaxies dance apart at unimaginable speeds. The expansion of the universe explains why we can see only a finite portion of it. As space stretches, light from distant galaxies takes longer and longer to reach us, and at some distance, it becomes impossible for their light to arrive at all. This concept, the cosmic light horizon, defines the boundary of the observable universe. If we imagine a sphere centered on Earth, every point on the surface represents the farthest light that has managed to traverse space and time to reach us. Beyond this surface, the universe continues, potentially infinitely, but remains forever hidden from our view, moving away faster than light can ever bridge the gap. This distinction between the observable and the entire universe is subtle but crucial. The observable universe is not all there is. It is only what our instruments can detect, a consequence of both cosmic expansion and the finite speed of light. Understanding the size of the observable universe also requires confronting a strange and counterintuitive fact. Although the universe is 13.8 billion years old, the observable universe has a radius of 46.5 billion light-years, far greater than the age of the universe might suggest. The answer lies in the expansion of space itself. When the earliest photons were emitted, the universe was much smaller, but space has stretched enormously since then. These photons have traveled across expanding space for billions of years, and during that time, the distance they traverse has also grown. This is why the universe can appear to be larger than the simple multiplication of light speed by the universe's age would indicate. The concept of co-moving distance captures this idea. It accounts for the expansion of space and allows us to measure how far distant objects are today, not just how far their light traveled in the past. The discovery of the universe's expansion also set the stage for one of the most remarkable revelations of modern science, the cosmic microwave background, or CMB, a faint afterglow of the Big Bang itself. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, detected a uniform microwave signal coming from all directions in space, a noise that seemed to have no source on Earth or in the galaxy. This radiation turned out to be the remnant heat from the early universe, released when protons and electrons first combined to form neutral atoms roughly 380,000 years after the Big Bang. The CMB provided a snapshot of the infant universe, frozen in time, a direct line of evidence for both the age and the initial conditions of cosmic expansion. Subsequent measurements by missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck Observatory mapped the temperature fluctuations of the CMB with extraordinary precision, revealing the seeds of cosmic structure, tiny density variations that would eventually grow into galaxies, clusters, and the large-scale cosmic web we observe today. These discoveries confirm that the universe is not only expanding, but that it has a well-defined age and an extraordinary dynamic history etched into every photon that reaches us. Returning to the edge of the observable universe, the practical implication of these findings is both humbling and mind-boggling. If you were to set out today, traveling at the speed of light, to reach the most distant visible galaxies, you would find that the distance is constantly increasing as you travel. The very space you move through is stretching, carrying the galaxies farther away faster than you can close the gap. Even light, the ultimate cosmic speedster, is unable to catch up to this expansion in certain regions of space. This is a consequence of the universe's expansion being driven not only by the initial momentum from the Big Bang, but also by a mysterious force known as dark energy, discovered in 1998 through observations of distant Type 1a supernovae. Dark energy, which now makes up approximately 68% of the total energy content of the universe, acts as a kind of negative pressure, accelerating the expansion and ensuring that some regions of the cosmos will remain forever unreachable. The edge of the observable universe is, therefore, not just distant. It is effectively a moving target, one that recedes faster than any traveller could hope to reach. Hubble's original discovery of galactic recession was the first step in uncovering these staggering truths, but it is only the beginning. With each advance in telescopes and observational technology, we have peeled back new layers of cosmic understanding. Spectroscopic surveys of distant galaxies, like those conducted with the Sloan Digital Sky Survey and the Hubble Space Telescope, have mapped the large-scale distribution of matter across billions of light-years, revealing that galaxies are not randomly scattered, but organized into clusters, filaments, and vast voids. This cosmic web stretches across the observable universe, a structure that reflects the tiny fluctuations captured in the CMB and amplified by billions of years of gravitational evolution. Every point of light in these surveys is not only a star or galaxy, but also a marker of cosmic history, a witness to the expansion that Hubble first measured almost a century ago. To fully grasp the immensity of the observable universe, we must also confront the limits imposed by relativity. Einstein's theory of special relativity establishes that nothing can travel faster than light in a vacuum. This principle is absolute. It is not a limitation of our technology, but a fundamental law of physics. Therefore, no matter how advanced our spacecraft might become, no human or probe could ever overtake the expansion of the farthest galaxies. Yet paradoxically, space itself is not bound by this restriction. Regions of the universe beyond a certain distance, the so-called Hubble sphere, recede from us at superluminal speeds, carried along by the stretching of space. This is why the observable universe can extend far beyond 13.8 billion light-years, and why we speak of a radius of 46.5 billion light-years, rather than a smaller number that might naively correspond to the universe's age. All of this brings us back to the cold, awe-inspiring truth that opens our story. Even travelling at the speed of light, you could never reach the edge of the observable universe. It is not just a question of distance, it is a question of the nature of space itself. The universe is expanding, accelerating, and vast beyond comprehension. The edge is not a wall or a frontier waiting to be crossed. It is a horizon defined by time, light, and the geometry of an expanding cosmos. Beyond it lies more universe, possibly infinite, possibly structured in ways we cannot yet imagine, and yet inaccessible to us forever. This realization is the first step into the staggering scale of the cosmos, the stage upon which the next chapters of discovery, dark energy, inflation, cosmic horizons, and the limits of travel will unfold. It is a reminder that the universe is larger than any journey, more ancient than any memory, and more dynamic than any imagination, and that even as we measure it, we are only beginning to understand its true scale and scope. The redshift breakthrough. When you look up at the night sky, it seems tranquil, almost eternal. Stars glimmer, galaxies swirl silently in the dark, and the cosmos appears fixed, unchanging, timeless. But if you could step beyond your earthly perspective, if you could measure the light streaming from distant galaxies with the precision of a skilled astronomer, you would discover something far stranger than the apparent stillness. You would find that the universe is not at rest. Every galaxy beyond our own Milky Way is moving away from us, drifting across space at enormous speeds, stretching the fabric of the cosmos itself. This revelation, so counterintuitive that it stunned the scientific community when first discovered, comes to us through one of the simplest yet most powerful tools in astronomy: light. The light from distant galaxies carries hidden information about motion, distance, and the very structure of the universe. It is in the subtle shifts of light's color, imperceptible to the human eye, that the story of cosmic expansion is written. And it is in this story that we find the first breakthrough that would forever change our understanding of the universe, the redshift. At the heart of the redshift breakthrough is the Doppler effect, a principle familiar to anyone who has heard the wail of an ambulance siren pass by. As the siren approaches, the sound waves are compressed, producing a higher pitch. As it recedes, the waves stretch, lowering the pitch. This shift in frequency allows us to infer motion without seeing the source directly. In the context of light, a similar principle applies. Light emitted by a star or galaxy moving toward us is shifted slightly toward shorter wavelengths, toward the blue end of the spectrum, a phenomenon called blue shift. Conversely, light from an object moving away is shifted toward longer wavelengths, toward the red end of the spectrum, hence the term redshift. This concept, simple in principle, becomes profoundly significant when applied to objects separated from us by millions or even billions of light years. It transforms light from a passive illumination of distant objects into an active messenger, encoding information about the motion and distance of galaxies across the cosmos. In the early 20th century, astronomers were just beginning to map the stars and nebulae beyond the Milky Way, and the scale of the universe was a subject of heated debate. Were these nebulae merely clouds of gas within our galaxy? Or were they entire galaxies themselves, islands of stars scattered across an unfathomable expanse? Observing these objects was not enough. To understand their place in space, astronomers had to measure their motion. Spectroscopy provided the key. By passing light through a prism or diffraction grating, astronomers could spread it into a spectrum and identify characteristic absorption or emission lines corresponding to elements such as hydrogen, calcium, and sodium. These spectral lines acted like cosmic fingerprints, each unique and identifiable, providing a reliable reference for measuring shifts in wavelength. If the lines were displaced from their expected positions, it indicated motion toward or away from the observer, revealing the velocity of the celestial object with remarkable precision. The first systematic application of this technique to distant galaxies revealed a pattern that was both astonishing and revolutionary. In 1929, Edwin Hubble published his groundbreaking observation showing that nearly every galaxy beyond our own was receding from us. He had measured the spectra of galaxies, noting the displacement of their spectral lines, and calculated their velocities. What emerged was a stunning correlation. The farther a galaxy was, the faster it appeared to move away. This was not a subtle trend. It was consistent across dozens of galaxies, providing compelling evidence for a universe that was not static, but expanding. Hubble's work did not merely add detail to existing maps of the cosmos. It transformed the very framework within which we understand the universe, shifting the perspective from a static, eternal space to a dynamic, evolving one. Before Hubble's observational confirmation, the concept of cosmic expansion had already been explored theoretically. In 1927, Georges Lemaitre had derived mathematically, using Einstein's equations of general relativity, that the universe could not remain static. Lemaitre proposed that the observed motion of galaxies could be explained if space itself were stretching, carrying galaxies along with it. He even suggested that the universe began from a highly dense initial state, what we would later understand as the Big Bang. Hubble's measurements provided the empirical support that Lemaitre's equations lacked, linking theory and observation in a way that would revolutionize cosmology. Together, their work established a new paradigm. The universe is expanding, and this expansion can be measured, quantified, and traced through light itself. The technique of measuring redshift relies on extremely precise observations. Astronomers identify spectral lines in the light from a galaxy and compare them to the same lines measured in laboratories on Earth. If the lines are shifted toward red, the galaxy is receding. If toward blue, it is approaching. The amount of shift, denoted by the variable z, can be converted into a velocity using well-established formulas derived from the Doppler effect and the principles of relativity. For nearby galaxies, the velocity is roughly proportional to z, but for extremely distant galaxies, the relationship becomes more complex, requiring relativistic corrections. By combining redshift measurements with estimates of distance, astronomers can map the expansion of the universe across space and time, revealing a cosmos that is both vast and dynamic. One of the most striking implications of the redshift is that it provides a way to measure distances in the universe on an incomprehensible scale. Unlike measuring distances in the solar system, where we can rely on radar or direct observation, intergalactic distances must be inferred from light itself. Redshift, when calibrated with other methods such as Cepheid variable stars or supernovae, allows astronomers to determine how far away a galaxy is with astonishing accuracy. It is through this process that we can state confidently that the observable universe has a radius of approximately 46.5 billion light-years and a diameter of roughly 93 billion light-years. These numbers are staggering, yet they are not abstract. They are directly derived from the light streaming from the farthest reaches of the cosmos, measured and interpreted through the principles first applied by Hubble and Lemaitre. As we examine redshift more closely, we find that it is not merely a measurement of motion, but a window into the history of the universe. Light from distant galaxies has traveled for billions of years, carrying with it a record of the state of the universe at the time of emission. When we observe a galaxy with a redshift of z equals 1, for example, we are seeing it as it existed roughly 7 billion years ago, half the current age of the universe. A galaxy with a redshift of z equals 6 existed when the universe was less than 1 billion years old. Each shift in wavelength is a journey back in time, revealing the structure, composition, and behavior of galaxies as they evolved across cosmic history. Redshift transforms our telescopes into time machines, allowing us to study the universe as it was, not just as it appears today. The practical challenges of measuring redshift cannot be overstated. Astronomers must account for the effects of interstellar and intergalactic matter, which can absorb or scatter light, distorting the observed spectra. They must correct for the motion of the Earth, the rotation of our planet, and its orbit around the Sun, all of which introduce additional velocity components. They must also distinguish between peculiar velocities, motions of galaxies relative to their local environment, and the overall recession due to cosmic expansion. These complexities require meticulous observation, careful calibration, and sophisticated modelling. Yet despite these challenges, the correlation between distance and redshift remains robust, providing some of the most reliable evidence for the expansion of the universe. Redshift also reveals a subtle but profound distinction between different types of motion. In our everyday experience, motion occurs through space. A car moves along a road. A plane flies through the air. In the universe, galaxies appear to recede from us, not because they are moving through space in the traditional sense, but because the fabric of space itself is expanding. This cosmological redshift is fundamentally different from a Doppler shift caused by motion through space. It is a stretching of wavelengths caused by the stretching of space itself, an effect predicted by general relativity and confirmed by observation. As space expands, it carries galaxies along with it, stretching the light they emit and shifting it toward the red end of the spectrum. This insight transformed our understanding of motion on cosmic scales, revealing a universe in which space itself is dynamic and evolving. The implications of the redshift breakthrough extend beyond the motion of galaxies. By measuring redshift across a range of distances, astronomers can infer the rate of expansion of the universe, estimate its age, and model its future evolution. Redshift provides a foundation for understanding cosmic structure, the formation of galaxies, and the distribution of matter on the larger scales. It allows scientists to trace the history of the universe from its earliest moments to the present day, linking observation with theory in a coherent framework. Without redshift, of cosmic expansion, dark energy, and the Big Bang would remain hidden, and our knowledge of the universe would be profoundly limited. Most importantly, redshift shows us that the universe is not static, not eternal, not confined to what we can see with the naked eye. Every galaxy is moving, every photon is traveling across an expanding sea of space, and every measurement of light carries with it motion, distance, and time. Hubble's law and the expanding universe. If the discovery of redshift opened our eyes to the motion of galaxies, then Hubble's law gave the universe its measure, transforming a bewildering pattern of recession velocities into a simple, elegant equation that captures the very rhythm of cosmic expansion. Imagine standing on a vast, invisible stage, looking outward in every direction. Galaxies are moving away, some slowly, some faster, but the speed at which they recede is not random, it is proportional to their distance. The farther a galaxy is, the faster it moves. This is the essence of Hubble's law, expressed mathematically as v equals h0 times d, where v is the recession velocity of a galaxy, d is its distance from us, and h0 is the Hubble constant, a number that defines the rate of expansion of the universe. It is an equation of astonishing simplicity that encodes a profound truth. The universe itself is stretching, and this stretching governs everything on the larger scales. The path to this discovery began in earnest with the careful observations of Edwin Hubble at the Mount Wilson Observatory in the late 1920s. Hubble combined measurements of galaxy distances obtained through methods such as Cepheid variable stars, pulsating stars whose intrinsic brightness allows precise distance calculations, with spectroscopic measurements of their redshifts. He noted that galaxies with greater redshifts, which we now understand as faster recession velocities, were systematically farther away. The relationship was remarkably linear. It was a breakthrough not only in astronomy, but in human understanding. The universe was not static, unchanging, or eternal in the classical sense. It was dynamic, growing, and structured by a fundamental expansion. This simple proportionality, now immortalized as Hubble's law, allowed astronomers to quantify the rate of expansion and estimate the age and scale of the cosmos in a way never before possible. Hubble's observational confirmation came just 2 years after Georges Lemaitre had derived the theoretical expansion of the universe from Einstein's general relativity equations in 1927. Lemaitre's work was revolutionary. He proposed that if the universe were expanding, then the recession of galaxies could be explained mathematically, and he even suggested a relationship between distance and velocity, essentially predicting what Hubble would later observe. Lemaitre went further, hypothesizing that the universe originated from a single, extremely dense point, what would later be understood as the initial singularity of the Big Bang. Hubble's empirical measurements, independent yet complementary, provided the observational evidence that Lemaitre's theoretical framework required. Together, their contributions transformed cosmology from a speculative endeavor into a precise, measurable science. The Hubble constant, h0, captures the rate at which the universe expands. Determining its precise value, however, has proven to be one of the most challenging and intriguing problems in modern cosmology. Different methods produce slightly different results, a tension that has only intensified with the advent of advanced observational techniques. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, taken by the European Space Agency's Planck Observatory, suggest a value of roughly 67 kilometers per second per megaparsec. In contrast, measurements based on local observations, including distances to supernovae and Cepheid variables conducted by NASA and other observatories, yield a higher value of approximately 73 kilometers per second per megaparsec. This discrepancy may seem small numerically, but it has profound implications. It could point to new physics beyond our current understanding, perhaps involving modifications to dark energy, unaccounted for matter distributions, or subtle effects in the early universe that we have yet to comprehend. Understanding Hubble's law also provides a means to estimate the age of the universe. If the expansion rate were constant, then the reciprocal of the Hubble constant would give the approximate time elapsed since the Big Bang. With current values, this corresponds closely to the 13.8 billion years determined independently from observations of the cosmic microwave background. This connection between expansion rate and cosmic age underscores the deep power of Hubble's insight. By measuring how fast galaxies recede, we are indirectly measuring the lifetime of the universe itself, turning a simple velocity-distance relationship into a cosmic clock. The significance of Hubble's law extends beyond numbers and measurements. It provides the foundation for our understanding of the Big Bang, the hot, dense state from which all space, time, and matter emerged. The linear relationship between velocity and distance implies that if we were to reverse the expansion, all galaxies would converge to a single point. This is not mere speculation. It is a direct consequence of the observed expansion, confirmed by the redshift data meticulously collected and analysed by astronomers over decades. The Big Bang is not a philosophical idea or a metaphor. It is a scientific conclusion derived from precise measurements, redshift data, and the application of Einstein's general relativity. Hubble's law also illuminates the scale and structure of the cosmos. When we observe galaxies billions of light years away, we are not merely seeing distant points of light. We are witnessing epochs of cosmic history long before our own solar system formed. The farther we look, the closer we come to the early universe, a period when galaxies were forming, stars were igniting for the first time, and cosmic structures were taking shape. Hubble's law allows astronomers to map these epochs, connecting distance with time and providing a coherent narrative of cosmic evolution. Through this lens, every galaxy becomes a historical marker, a witness to billions of years of expansion, growth, and transformation. The expansion implied by Hubble's law also introduces the concept of a dynamic universe governed by laws that extend beyond our immediate intuition. Space itself is not a passive stage. It is active, stretching between galaxies, influencing motion and shaping the large-scale structure of the cosmos. The metric expansion of space, a term that arises from general relativity, explains why galaxies can recede from us faster than the speed of light without violating the laws of physics. It is not motion through space, but the expansion of space itself that drives these velocities. This distinction is crucial, allowing us to understand phenomena that initially seem impossible, such as the existence of galaxies moving away faster than light in a universe expanding under Hubble's law. Hubble's work also paved the way for an era of precision cosmology. By measuring the relationship between redshift and distance across vast cosmic scales, astronomers can probe the universe's composition, the influence of dark matter, and the role of dark energy in accelerating expansion. The Hubble constant is not just a number, it is a key to unlocking the forces shaping the cosmos. Small variations in its value inform models of cosmic history, including when galaxies formed, how clusters coalesced, and how the expansion rate has changed over billions of years. This quantitative approach transforms astronomy from observation into predictive science, allowing researchers to model the universe with extraordinary fidelity. One of the most compelling consequences of Hubble's law is the realization that the universe has no center. Expansion occurs uniformly in all directions. Every observer, regardless of location, sees the same pattern of galaxies moving away. This is a counterintuitive idea. Unlike an explosion on Earth, where fragments radiate outward from a central point, the universe's expansion is embedded in space itself. There is no privileged vantage point, no central galaxy from which all others recede. Every galaxy perceives itself as the center of its observable universe, with the same recession pattern manifesting in every direction. Hubble's law, therefore, not only quantifies motion, but reshapes our conceptual understanding of space, scale, and position in the cosmos. The tension in the value of the Hubble constant highlights that even in a seemingly simple equation, mysteries remain. The discrepancy between early universe measurements from the cosmic microwave background and local universe observations suggests that our current understanding is incomplete. Some cosmologists propose that dark energy may have evolved over time, altering the expansion rate in ways we cannot yet fully account for. Others suggest the possibility of unknown forms of matter or subtle deviations in the physics governing the early universe. These debates are ongoing, and each new measurement, each refined observation, adds a piece to the puzzle. Hubble's law is not a closed chapter. It is an evolving framework, a foundation upon which the next century of cosmology will build. Hubble and Lemaitre's combined contributions also underscore the interplay between theory and observation. Lemaitre's equations suggested expansion. Hubble's observations confirmed it. Theory predicted the motion, observation measured it. Together, they demonstrate a fundamental principle of science, that our understanding of the universe emerges from the dialogue between mathematics, physics, and empirical evidence. This synergy is evident in every redshift measurement, every galaxy mapped, and every calculation of the Hubble constant. It is a story of insight, diligence, and the relentless human drive to quantify and comprehend the cosmos. Hubble's law transforms how we understand the passage of time on a cosmic scale. The farther we look, the farther back in time we see, and the faster galaxies appear to recede. Light from distant galaxies has travelled billions of years to reach us, revealing conditions from the early universe and enabling us to reconstruct its history. The linear relationship between distance and velocity allows us to chart the evolution of the cosmos, tracing back to the epoch when space itself was young, hot. Hubble's law is a temporal as well as spatial map, connecting velocity with the age and scale of the universe and providing a framework for interpreting every photon that reaches our telescopes. In practical terms, Hubble's law also guides the design of observational programs, the allocation of telescope time, and the interpretation of astronomical data. It allows astronomers to predict the redshift of a galaxy based on its distance, or conversely, to estimate distance from measured redshift. This predictive power is essential for planning deep sky surveys, targeting specific cosmic epochs, and studying phenomena such as galaxy formation, cosmic filaments, and the large-scale distribution of matter. It underpins the work of modern observatories, from NASA's Hubble Space Telescope to the Planck mission, enabling scientists to probe the universe with unprecedented precision. Hubble's law is more than an equation. It is a lens through which we perceive the universe's grand narrative. It tells us that the cosmos is vast, dynamic, and evolving, that galaxies are not stationary ornaments, but participants in a continuous, measurable expansion, and that the universe itself has a beginning, a singularity from which space, time, and matter emerged. By connecting distance, velocity, and time, Hubble's law provides a quantitative framework for understanding the scale, age, and history of the cosmos, offering a foundation for all modern cosmology. It is a testament to human curiosity, ingenuity, and the power of observation, revealing a universe that is at once comprehensible, astonishing, and infinitely vast. Cosmic microwave background. If you could travel far enough into space, far beyond the brightest galaxies and the swirling clusters of stars, and then stop, stand still, and listen to the universe itself, you would hear a whisper of light that has been travelling for nearly 14 billion years. It is faint, almost ghostly, barely detectable, and yet it carries the story of the universe's earliest moments. This is the cosmic microwave background, or CMB, a signal so old that it predates galaxies, stars, and even atoms as we know them. It is the afterglow of the Big Bang, The heat left over from the time when the universe was a hot, dense and expanding fireball stretched across the cosmos and cooled to a chilly 2.725 degrees Kelvin. That temperature, barely above absolute zero, tells us that the universe has expanded and cooled over billions of years, from a searing beginning to the vast, cold cosmos we see today. The CMB is like a snapshot, frozen in time. It comes from a moment about 380,000 years after the Big Bang, when the universe was just a baby, less than 500,000 years old. Back then, everything was different. Space was filled with a hot plasma, a glowing soup of protons, electrons, and photons, all interacting constantly. Light could not travel freely. Every photon was constantly bouncing off charged particles trapped in a chaotic dance. The universe was opaque, a foggy, glowing mist where nothing could move, unimpeded. But then came the recombination epoch, a moment of transformation. Electrons combined with protons to form neutral hydrogen atoms. Freed from the constant scattering, photons could finally travel across space. This release of light is what we now detect as the CMB, a faint, uniform radiation bathing the universe in all directions. It is the oldest light we can observe, a direct message from the cosmos's infancy, telling us how the universe looked when it first became transparent. Even though the CMB is remarkably uniform, it is not perfectly smooth. Tiny variations, or anisotropies, appear across the sky. These variations are subtle differences in temperature, only a few millionths of a degree, yet they are incredibly important. They represent slight differences in density in the early universe. In some regions, matter was just a little denser than average. In others, just a little less. Over billions of years, gravity amplified these small fluctuations, pulling matter together in some places and leaving voids in others. The result is the cosmic web we see today. Galaxies, clusters, and superclusters forming in patterns that mirror the tiny ripples preserved in the CMB. In other words, the seeds of all the large-scale structures we see in the universe were already present in these tiny temperature differences, written into the radiation long before the first stars shone. The story of mapping these anisotropies begins in earnest with NASA's Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP measured the CMB with unprecedented precision. It scanned the sky for temperature differences as small as 100,000th of a degree, revealing the detailed structure of the early universe. The data from WMAP provided a full sky map of the CMB, showing a delicate pattern of hot and cold spots, ripples frozen in the fabric of space-time. Scientists could see the imprints of sound waves or acoustic oscillations traveling through the primordial plasma. These ripples were caused by competing forces, gravity pulling matter together and radiation pressure pushing it apart. The result was a cosmic symphony of oscillations, preserved in the pattern of temperature fluctuations that WMAP captured. Following WMAP, the European Space Agency launched the Planck satellite, a mission designed to refine and expand the measurements even further. Planck mapped the CMB with higher resolution and greater sensitivity, confirming and sharpening the patterns detected by WMAP. The Planck data revealed the tiniest details, helping scientists understand not just the distribution of matter, but also the composition of the universe. From these measurements, cosmologists could determine the proportions of normal matter, dark matter, and dark energy, as well as the geometry of space itself. The CMB became a blueprint, a cosmic fingerprint, allowing researchers to reconstruct the universe's early history with remarkable accuracy. The temperature of the CMB, 2.725 Kelvin, is more than a number. It is a relic of the universe's expansion. When the universe was first transparent, the photons released were far hotter, with temperatures reaching thousands of degrees. As space expanded over billions of years, the wavelength of this radiation stretched, lowering its energy and cooling it to the microwaves we detect today. Observing this radiation is like looking at a photograph taken with the universe's oldest camera, with each photon carrying a message from the past, slightly stretched and dimmed, but still readable. The CMB also provides insight into fundamental processes in the early universe. Photon decoupling, the moment when photons began travelling freely, marks the boundary between a dense, opaque plasma and the transparent cosmos. It defines a horizon we cannot see earlier with light because photons from before this epoch were trapped in the plasma. To probe earlier times, scientists must rely on other messengers like neutrinos or gravitational waves. But the CMB remains the oldest electromagnetic signal we can observe. Its uniformity across the sky also provides evidence for the isotropy of the universe, the idea that the cosmos looks roughly the same in all directions. Any significant deviation from uniformity would have suggested a universe far more chaotic than what we see. The tiny anisotropies are enough to form galaxies, but do not disrupt the overall smoothness, revealing a delicate balance in the early universe's evolution. The anisotropies in the CMB are also a window into physics at scales impossible to reproduce on Earth. The density fluctuations imprinted in the radiation carry the signature of quantum processes occurring when the universe was fractions of a second old. During inflation, a brief period of rapid expansion, quantum fluctuations were stretched to cosmic scales. These fluctuations set the stage for the patterns we see in the CMB and ultimately guided the formation of galaxies and clusters. In this way, the CMB is a bridge between the smaller scales of quantum physics and the larger scales of cosmology, connecting the early universe to the sprawling structures visible today. Measuring these anisotropies is far from trivial. The signal is incredibly faint, easily drowned out by radiation from the Milky Way, nearby galaxies, and even our own instruments. Satellites like WMAP and Planck had to operate in deep space, far from Earth's atmosphere and interference, to capture the CMB with clarity. They used highly sensitive microwave detectors and scanned the sky repeatedly to build a complete map. Each measurement was carefully calibrated, checked, and corrected for foreground noise. The resulting maps revealed not just temperature variations, but also polarization patterns, subtle alignments in the orientation of light that provide additional clues about the early universe. Polarization helps scientists probe the distribution of matter and the behavior of radiation during recombination, offering another layer of insight into the cosmos's infancy. The recombination epoch itself is fascinating. Before this moment, the universe was a hot plasma, and photons were trapped in constant interaction with charged particles. Once electrons combined with protons to form neutral hydrogen, photons could finally travel without scattering. This decoupling released the CMB, allowing light to propagate freely through the universe. The universe transitioned from opaque to transparent in a relatively short time, and the photons from that moment have been travelling ever since, stretched and cooled by the expanding cosmos. Every point in the CMB map corresponds to a region of space at that precise moment, a literal photograph of the universe's first visible light. The tiny differences in temperature, the anisotropies, are not random noise. They encode the blueprint for cosmic structure. Regions slightly denser than average eventually pulled in more matter through gravity, growing into galaxies and clusters. Less dense regions became cosmic voids. The patterns we see in the CMB correspond to these primordial density fluctuations. Studying the distribution, size, and amplitude of these fluctuations allows scientists to predict the large-scale structure of the universe billions of years later. The CMB, in essence, provides the seed patterns from which all cosmic structures grew. Beyond structure, the CMB offers a window into the composition of the universe. Analysis of the anisotropies by WMAP and Planck has revealed the relative amounts of ordinary matter, dark matter, and dark energy. The precise pattern of hot and cold spots combined with models of cosmic evolution indicates that normal matter makes up only about 5% of the universe, dark matter about 27%, and dark energy roughly 68%. This is information we could not have obtained from galaxies alone. The CMB is a record of the universe before stars and galaxies dominated, providing a pristine laboratory for understanding the forces and matter shaping everything we see today. Acoustic oscillations, patterns seen in the CMB, are also remarkable. The early plasma was subject to waves caused by the tug-of-war between gravity and radiation pressure. Gravity tried to pull matter together, radiation pushed it apart, creating ripples that travelled through the primordial plasma. These sound waves left imprints in the CMB, tiny variations in temperature and density. When we study the spacing and size of these ripples, we gain insight into the universe's expansion, composition, and curvature. Every bump, every pattern, tells a story about the physics governing the universe at an age of mere hundreds of thousands of years. The CMB also acts as a cosmic ruler. By comparing observed patterns with theoretical models, scientists can measure distances in the universe, check the rate of expansion, and test predictions of cosmology with astonishing precision. This has allowed measurements of the Hubble constant, the geometry of space, and the amount of dark matter and dark energy present in the cosmos. The radiation that began as an almost uniform glow has become a tool to map the universe, to measure its properties, and to test the fundamental laws of physics across scales that are unimaginable on Earth. WMAP and Planck didn't just map the CMB, they transformed it into a tool for discovery. The data allowed scientists to refine models of inflation, to test hypotheses about the early universe, and to predict the distribution of galaxies billions of years later. They revealed subtle anomalies and patterns that continue to puzzle researchers, hinting at phenomena beyond the standard model of cosmology. The CMB is more than a relic. It is an active field of research, a source of questions as much as answers. Every photon in the CMB has travelled for nearly 14 billion years, stretching across the expanding universe, passing through regions of space that would eventually become galaxies, stars, and planets. By capturing and analysing this light, scientists have unlocked a window to the universe's earliest moments, seeing a universe that was hot, dense, and uniform, yet containing the seeds of all future structure. The measurement of 2.725 Kelvin is a reminder of cosmic cooling, of the journey from a blazing, opaque infancy to the cold, transparent cosmos we inhabit today. The CMB also shows the remarkable uniformity of the universe on the larger scales. While galaxies cluster and cosmic voids form, the radiation itself is isotropic to an astonishing degree. Tiny fluctuations exist, but overall, the universe looks the same in every direction. This isotropy supports the idea that the universe underwent inflation, a period of rapid expansion that smoothed out irregularities and created the nearly uniform radiation that WMAP and Planck mapped. It is a hint at processes that occurred at timescales and energies far beyond anything achievable in laboratories, yet whose effects we can read billions of years later. Expansion during photon travel. When a photon leaves a distant galaxy, it begins an incredible journey across the universe. It travels at the ultimate speed limit, the speed of light, covering vast stretches of space. But here's the twist. The space it travels through is not stationary. While the photon moves, space itself is expanding. The distance between galaxies is stretching, carrying the photon along as it races toward us. This means that the light we receive today has travelled farther than it would seem if space were fixed. The photon's path is not through a static backdrop. It is through a universe that is growing, stretching, and changing. And that growth affects how we measure distances and understand the cosmos. Imagine a photon leaving a galaxy when the universe was very young, just a few billion years old. At the moment of emission, the galaxy was much closer to us than it is now. As the photon moves, space expands, increasing the distance between the photon and our galaxy. By the time the photon reaches Earth, the universe has expanded enormously, and the distance between us and the source galaxy has grown far beyond what the photon experienced while traveling. This is why the actual travel time of a photon and the current distance to its source are not the same. Astronomers call this difference the co-moving distance. The photon's journey records the universe's growth along its path, giving us a map of cosmic expansion as it happened. This stretching of space also explains why light from distant galaxies is redshifted. The wavelengths of photons stretch as the space they travel through stretches. A photon emitted in visible light billions of years ago may arrive at Earth as infrared or microwave radiation because space itself has expanded. The redshift we observe is a direct measure of how much the universe has grown since the photon was emitted. Higher redshift means the photon travelled through more expanding space, and thus the emitting galaxy was farther away when the light left it. Each photon is a historical record, not just of its source, but of the universe's expansion along its path. The difference between the distance when the photon was emitted and its current distance is mind-boggling. Light that left its source when the universe was only a fraction of its present age has been stretched across billions of years, while space itself expanded under its feet. If we imagine freezing the universe at the moment of photon emission, the galaxy might have been just a few billion light years away. Today, due to the continuous expansion during the photon's travel, the same galaxy is tens of billions of light years away. The journey of the photon is therefore both a measurement of distance and a record of the universe's dynamic nature. Photon travel also highlights the non-intuitive nature of cosmological distances. Unlike measuring distances on Earth, where the length of a road is fixed, cosmic distances are constantly changing. The universe expands even while light is in motion, meaning that the photon never experiences space as static. This stretching must be accounted for when mapping galaxies and determining the size of the observable universe. It's not enough to just measure how long light has travelled. We must also understand how the space between has grown. This is why astronomers differentiate between the light travel distance, the distance light has travelled since emission, and the co-moving distance, which accounts for the ongoing expansion of space. The expansion during photon travel also explains why we can see galaxies that are technically receding faster than light. In the expanding universe, galaxies at extreme distances are carried away by space itself. Their recession velocities, due to the stretching of space, can exceed the speed of light, and yet photons emitted by these galaxies billions of years ago can still reach us. These photons were emitted when the galaxies were much closer. And although the galaxies have since moved farther apart, the light gradually makes its way through the stretching space. The photon's journey is a cosmic relay, navigating an expanding arena and eventually reaching our telescopes. This process affects every observation of distant objects, from quasars to the faint afterglow of the cosmic microwave background. When we observe the CMB, we are seeing photons that left the universe just 380,000 years after the Big Bang. The original distance from Earth was far smaller than the distance those photons have travelled through expanding space to reach us today. The expansion of space stretches the wavelengths and increases the effective distance, giving us a present co-moving distance that reflects the universe's growth over billions of years. The CMB is therefore both a map of the early universe and a demonstration of cosmic expansion in action. Photon travel during expansion also underlines the importance of redshift as a cosmological tool. The more the universe has expanded while a photon is in flight, the greater its redshift. By measuring the redshift, astronomers can infer both the distance the photon has travelled and the scale of expansion during its journey. This allows us to reconstruct the history of the universe's growth and connect ancient light with the structure of the cosmos we see today. Every distant galaxy and every photon carries this information, making the study of light an investigation of both space and time. The stretching of space during photon travel also affects how we measure cosmic time. A photon travelling from a galaxy billions of light years away was emitted when the universe was much younger. By observing the photon now, we are looking back in time, but the universe has not only aged, it has grown. The expansion during travel means that distances at the time of emission were smaller, and the universe's scale factor has increased continuously. The light we see is a record of the universe at one scale factor, while its current position corresponds to a much larger scale factor. This interplay between light, time, and expansion is a key principle of cosmology, shaping our understanding of how the universe evolves. This also explains why the observable universe is so much larger than the age of the universe might suggest. The universe is about 13.8 billion years old, so naively, one might think the farthest light could have travelled is 13.8 billion light years. But during that journey, space expanded dramatically. Photons that left galaxies billions of years ago traversed an ever-stretching cosmos, so the current distance to those galaxies, the co-moving distance, is now roughly 46.5 billion light-years. The expansion during photon travel transforms our perception of distance and highlights the dynamic nature of space itself. Even relatively nearby galaxies illustrate this principle. A galaxy with a redshift corresponding to several billion light-years away emitted its photons when the universe was smaller. The photons travelled across an expanding medium, and the space between has stretched since emission. When astronomers calculate distances today, they take into account this stretching to determine the present co-moving distance. Without accounting for expansion during photon travel, we would drastically underestimate cosmic distances and misunderstand the universe's size and structure. The journey of photons through expanding space also emphasizes the interconnectedness of cosmic events. Recombination, photon decoupling, and the formation of density fluctuations all occurred while space was stretching. Light released during these events did not travel through a fixed backdrop, but through a universe that was growing in real time. This continuous expansion affects not just distances, but the evolution of structure, the propagation of radiation, and the interpretation of all observations. Every photon is therefore a messenger carrying information about both the early universe and the dynamic stage it travelled across. Photon travel during expansion is not just theoretical, it is observed directly in redshifted light. Every measurement of redshift, from nearby galaxies to the cosmic microwave background, confirms that space has been expanding while light was in transit. The stretching of wavelengths corresponds exactly to the stretching of space, providing a consistent and measurable record of the universe's growth. This is why cosmologists can combine redshift, distance, and light travel time to map the history of expansion, reconstructing a dynamic cosmic timeline from the faintest photons arriving in our detectors today. The stretching of space during photon travel also demonstrates the universe's lack of a center. Photons from all directions show expansion. No matter where a photon originates, its path is lengthened by the growth of space along the way. Every observer, anywhere in the universe, would see the same pattern of receding galaxies. Expansion is uniform, and photon travel confirms it. There is no central point from which everything moves away. The expansion is embedded in space itself, affecting all photons equally and consistently across the cosmos. Every distant galaxy we observe illustrates this principle, Light that left billions of years ago shows redshift, corresponding to the expansion that occurred while it was in transit. The difference between the emission distance and the current co-moving distance is enormous. Photon travel during expansion stretches not just wavelengths, but our sense of scale. A galaxy that was once relatively close now resides tens of billions of light years away, a testament to the continuous growth of space while light was moving through it. Even the cosmic microwave background is shaped by this effect. The photons we detect today left the universe at just 380,000 years old, when the scale of the cosmos was tiny compared to now. During their journey, space expanded tremendously, stretching the distance and the wavelengths of light. The CMB's redshifted microwaves are direct evidence of expansion during photon travel, showing that light is not merely moving through space. It is moving through a universe that is growing beneath it. Photon travel also reveals the importance of cosmological models. To convert redshift into distances and map the universe's structure, astronomers must account for the expansion that occurred during the light's journey. Models of cosmic expansion, based on Hubble's law, general relativity, and the observed composition of the universe, allow scientists to calculate how far galaxies have moved while light travelled. Without this understanding, distances would be misrepresented, and our picture of the universe would be distorted. Co-moving distance explained. Light travelling across the universe gives the illusion of moving through a fixed stage, but in reality, the stage itself is stretching. Co-moving distance is the tool cosmologists use to account for that stretching. It measures the distance between 2 points in space, factoring in the universe's expansion. Unlike simple light travel distance, which only counts how long a photon has been travelling, co-moving distance represents how far apart 2 points are right now, as if we could freeze the universe at the present moment and measure it. Using this framework, astronomers have determined that the radius of the observable universe is approximately 46.5 billion light-years, giving a full observable diameter of about 93 billion light-years. That scale is immense, far beyond what the simple age of the universe might suggest, because the universe has continued expanding while photons were in transit. The concept of co-moving distance relies on the scale factor, denoted as AT. This number describes how the size of the universe changes over time. At the moment of the Big Bang, AT was effectively 0. Today, it is normalized to 1. As the universe expands, the scale factor grows, stretching the distances between galaxies. If a galaxy was 1 unit away at an earlier time, its present co-moving distance is that original unit multiplied by the ratio of the scale factors, showing how far apart it has become due to expansion. The scale factor is central to cosmology because it allows scientists to connect the light emitted in the past with the current structure of the universe. When a photon leaves a galaxy, the scale factor is smaller. By the time it arrives on Earth, AT has grown, increasing the effective distance the light has travelled. Co-moving distance captures this growth, giving a more accurate representation of space than the naive measure of travel time alone. Metric expansion underpins this concept. The universe does not expand like an explosion from a centre point, sending galaxies outward. Space itself stretches uniformly, increasing distances between all objects without a defined centre. Galaxies are carried along with the stretching of the fabric of space, which is described mathematically by the Friedmann-Lemaitre-Robison-Walker metric. This metric allows cosmologists to calculate distances across the expanding universe and to convert observed redshifts into present-day co-moving distances. In other words, when a galaxy is receding at an incredible speed, that speed is not motion through space, but the expansion of space itself. Co-moving distance captures this nuance, providing a framework that reflects the true geometry of the universe. When we observe distant galaxies or the cosmic microwave background, the distinction between emission distance, light travel distance, and co-moving distance becomes critical. A photon, from a galaxy 13 billion light-years away was emitted when the universe was much smaller. Its travel time corresponds to 13 billion years, but because space stretched while the photon travelled, the present co-moving distance to that galaxy is far larger, approximately 46 billion light-years. Similarly, the cosmic microwave background was emitted when the universe was only 380,000 years old. The photons have travelled for almost 13.8 billion years. Yet the regions of space where those photons originated are now separated from us by roughly 46.5 billion light-years. Co-moving distance reconciles these differences, showing the actual scale of the universe at present. The scale factor also explains cosmological redshift. Redshift is not just a measure of velocity, it reflects how much the universe has expanded while the photon was travelling. If a photon is emitted when the scale factor was 0.1, the universe has grown tenfold by the time we observe that light. This stretching of space stretches the wavelength, shifting it toward the red end of the spectrum. High redshift galaxies, those observed at Z greater than 7, emitted light when the universe was tiny. Their co-moving distances are enormous today, even though the photons spent only a fraction of the universe's age travelling. Because co-moving distance depends on the scale factor, it also captures the effect of dark energy. The universe's expansion is not constant. It has accelerated over time due to dark energy. This acceleration means that the scale factor grows faster in recent epochs than it did in the early universe. For photons travelling billions of years, this means the stretching of space is not linear. Co-moving distance calculations must integrate this changing rate of expansion, taking into account the relative contributions of dark energy, matter, and radiation. It is this integration that allows astronomers to convert redshift into accurate distances and to map the observable universe in 3 dimensions. Metric expansion also clarifies why galaxies beyond a certain distance appear to recede faster than light. A galaxy at a co-moving distance greater than a particular threshold may have a recession velocity that exceeds c, the speed of light. This does not violate relativity because the galaxy is not moving through space faster than light. Rather, the space between us and the galaxy is stretching. Photons emitted from such galaxies can still reach us if they were emitted when the galaxy was closer and the expansion rate was slower, allowing the light to eventually navigate the expanding space. Co-moving distance helps visualize this process by providing a frozen snapshot of where galaxies are today relative to one another, regardless of the expansion they experienced while photons were traveling. The 46.5 billion light-year radius is derived using these principles. By integrating the scale factor over cosmic time, scientists calculate the present separation of objects whose light we now see. The observable diameter of 93 billion light-years represents the full span of the universe, from one edge of the observable horizon to the opposite edge. This number is not arbitrary. It comes from precise models of expansion, observations of redshift, measurements of the Hubble constant, and the cosmic microwave background. The observable universe is effectively a sphere centered on the observer, but because metric expansion has no preferred direction or center, every observer anywhere in the universe would measure the same co-moving radius. The concept of co-moving distance also informs studies of large-scale structure. Clusters of galaxies, filaments, and voids are mapped using this framework. The CMB anisotropies provide the initial conditions, showing density fluctuations at early times. As space expanded, these fluctuations grew, shaping the cosmic web. Co-moving distance allows astronomers to calculate how far structures have moved since the emission of light, connecting the early universe with the structures we see today. Without this approach, understanding the formation of galaxies, clusters, and superclusters across billions of years would be nearly impossible. Observations of supernovae, galaxy surveys, and the CMB all rely on co-moving distance. When plotting the positions of galaxies in a three-dimensional map, astronomers convert redshifts into co-moving coordinates. This creates a static snapshot of the universe at the present scale factor, even though the photons were emitted billions of years ago. This approach is essential for studying correlations between galaxies, mapping voids, and analysing the distribution of dark matter. Co-moving distance translates the dynamic, stretching universe into a usable framework for measurement and visualization. The scale factor AT also enables simulations of cosmic evolution. By assigning scale factors to different epochs, researchers can model the expansion, the growth of structure, and the development of galaxies over time. The initial density fluctuations measured in the CMB are input into simulations, and the expansion of space is modelled using AT and the Friedmann equations. These simulations can then predict the large-scale structure we observe today, including galaxy clustering, cosmic filaments, and voids. Co-moving distance provides the backbone for comparing simulated and observed structures, linking the early universe with the present-day cosmos. Metric expansion demonstrates the universe's uniformity and isotropy. Unlike explosions with a centre and fragments moving outward, the universe expands uniformly in all directions. Co-moving coordinates make this clear. Galaxies are not flying away from a single point. The space between them is increasing uniformly. This means that the observable universe is spherical from any vantage point, with a radius of 46.5 billion light-years, even though the universe as a whole may extend far beyond what we can see. This uniform expansion is embedded in the equations of general relativity and confirmed through observation, from redshifts to the CMB. Co-moving distance also has practical implications for measuring the Hubble constant. The Hubble parameter at any epoch can be combined with scale factor calculations to determine how quickly space has been stretching. Observations at different redshifts, combined with the known expansion history, allow astronomers to infer the rate of expansion at different times. This makes co-moving distance not just a theoretical construct, but a fundamental tool for measuring the dynamics of the universe over cosmic history. The large-scale structure of the universe, when plotted in co-moving coordinates, reveals patterns that correspond directly to the physics of the early universe. Regions that were slightly over-dense at recombination became clusters and filaments. Underdense regions became voids. The scale factor translates the tiny variations measured in the CMB into present-day separations between galaxies. Without co-moving distance, it would be impossible to map the cosmic web or understand the evolution from uniform plasma to the structured cosmos we see today. Observing galaxies at extreme redshifts, such as Z greater than 10, illustrates the vast difference between emission distance and co-moving distance. Light from these galaxies was emitted when the universe was less than 500 million years old. The emission distance might have been a few billion light years, but the co-moving distance today is tens of billions of light years. These measurements confirm that light is travelling through a universe that is continuously expanding, and co-moving distance captures the current separation, reflecting the cumulative stretching of space over billions of years. Speed of light limitation. The speed of light is more than just a number. It is the ultimate cosmic speed limit, the maximum velocity at which information, energy, and matter can travel through space. Light moves at exactly 299,792 kilometers per second, or roughly 186,282 miles per second. At that speed, a photon could circle Earth's equator nearly 8 times in a single second. Across the vastness of space, this speed determines how quickly we can receive information from distant stars and galaxies. It is the measure that defines causality in the universe, the sequence of cause and effect, and sets the stage for how we understand distances, time, and the structure of the cosmos. Albert Einstein codified this limit in his theory of special relativity. One of the core principles is that no object with mass can accelerate to the speed of light in a vacuum. As an object approaches light speed, its energy requirement increases without bound. To push a spacecraft to even 99% of light speed would require immense energy, far beyond anything humanity can currently generate. At exactly light speed, the mass would be infinite, and infinite energy is physically impossible. This limitation is not a technological barrier, it is a law of nature. The speed of light is woven into the fabric of space-time itself, defining the way matter, energy, and information propagate through the universe. Special relativity also redefines our concepts of time and space. For objects moving near light speed, time slows down relative to stationary observers, a phenomenon known as time dilation. Distances along the direction of travel contract, a process called length contraction. These effects are not theoretical curiosities. They have been confirmed through countless experiments, from particle accelerators to precise atomic clocks on airplanes. Time, distance, and energy are linked by the speed of light, and nothing can break this universal limit. For the universe at large, this speed limit has profound consequences. Light from distant galaxies takes billions of years to reach us. When we observe a galaxy 10 billion light years away, we are seeing it as it existed 10 billion years ago. That light travelled at a fixed speed through space, carrying information across vast cosmic distances. Even for photons emitted during the earliest moments of the universe, the journey is constrained by this universal limit. No matter how powerful the source or how long the travel time, nothing can locally exceed 299,792 kilometers per second. This limitation shapes the observable universe itself. Because light can only travel so far in the age of the universe, approximately 13.8 billion years, there is a cosmic horizon beyond which we cannot see. Objects beyond this horizon emitted light that has not yet had time to reach us. The speed of light defines this boundary, determining the maximum distance from which electromagnetic signals can arrive. This is the fundamental reason the observable universe has a radius of roughly 46.5 billion light-years, even though the universe is older than 13.8 billion years. The combination of finite light speed and cosmic expansion sets the ultimate limits of our vision into the cosmos. The speed of light also underpins the concept of causality. No event can influence another faster than light can travel between them. If a star explodes 1,000 light-years away, we will not witness the supernova for a millennium. Until the photons arrive, the event is entirely causally disconnected from us. This cosmic delay is not just a curiosity. It is a fundamental property of space-time. Information cannot travel instantaneously, and the speed of light acts as the universal messenger, limiting the reach of influence and observation. Relativity makes it clear that faster-than-light travel is impossible locally. Tachyons, hypothetical particles that move faster than light, have never been observed. Experiments consistently confirm that mass-bearing objects are bound by the cosmic speed limit. Even photons, which travel at light speed, carry energy but no rest mass. Anything with mass accelerating toward light speed demands infinite energy, rendering local superluminal motion unattainable. Space itself, however, introduces a subtle nuance. While objects cannot move through space faster than light, space can stretch. This distinction sets the stage for understanding why the universe can grow in ways that seem to defy the speed of light, without violating relativity. The speed limit also constrains how fast signals and gravitational interactions propagate. Gravitational waves, ripples in space-time predicted by Einstein and first observed in 2015, travel at exactly the speed of light. This ensures that changes in gravitational fields propagate no faster than information can travel. When a star collapses into a black hole, its gravitational influence changes, but that information reaches distant observers only at light speed. This unifies electromagnetic and gravitational interactions under the same cosmic limit, reinforcing the fundamental role of 299,792 kilometers per second as the universal constant governing motion and communication. Even light from the most distant sources cannot escape this principle. Photons emitted from the cosmic microwave background 380,000 years after the Big Bang travelled through a universe that was already expanding. Their journey was limited by the speed of light locally, even as the space between them stretched. The expansion of the universe does not violate special relativity because it is the fabric of space itself that grows, not the motion of light through space. Nevertheless, the speed of light governs how quickly the information from those photons reaches us and sets the scale of what we can observe. The speed of light also frames our understanding of cosmic timelines. The universe is 13.8 billion years old, but light has been travelling through it for most of that time. Observing distant galaxies, quasars, and the CMB provides a time machine, taking us backward along light's journey. However, the finite speed ensures that there is a horizon to our vision. Even if the universe contains regions far beyond our reach, light from those regions has not yet arrived. The local speed limit is a boundary that transforms into a global horizon when considered on cosmological scales. Special relativity extends this limitation to motion within galaxies and star systems. No matter how powerful a spaceship or signal, travel faster than light through local space is impossible. Interstellar travel, even at near-light speeds, would take decades or millennia to reach neighbouring stars. This emphasises the gap between local speed limits and the expansion of space, a distinction that is crucial when understanding the universe at its larger scales. Galaxies are not moving through space faster than light. Rather, the space between them stretches. The speed limit applies locally, but cosmic expansion allows superluminal recession without violating relativity. Photon travel illustrates this principle clearly. Light from a galaxy billions of light years away was emitted when that galaxy was much closer. The photons moved at light speed relative to their immediate surroundings, while the universe itself expanded underneath them. The stretching of space increases the co-moving distance without requiring light to exceed its ultimate limit. This is why the universe can grow to a radius of 46.5 billion light-years, even though the speed of light is fixed, and the universe is only 13.8 billion years old. High-energy cosmic rays, the fastest known particles with mass, also demonstrate the limitations imposed by light speed. Despite travelling near C, these particles cannot exceed it, even when accelerated by massive astrophysical phenomena such as supernova remnants or black hole jets. Observations confirm that as velocities approach light speed, relativistic effects dominate, and no mass-bearing particle breaks the cosmic limit. The speed of light remains the boundary that defines motion, energy, and causality throughout the universe. Relativity and the speed of light also govern the behaviour of information transfer across space. Communication between spacecraft, satellites, and Earth is always delayed by light travel time. Even signals to the Moon take just over a second, while signals to Mars can take tens of minutes. Scaling this principle to intergalactic distances reveals enormous delays. Information from galaxies billions of light-years away requires billions of years to arrive, showing that the speed of light shapes not only observation, but the flow of information across cosmic time. The constancy of light speed is equally fundamental. Unlike sound, which travels faster or slower depending on the medium, Light in a vacuum is invariant. It travels at 299,792 kilometers per second, regardless of the observer's motion. This constancy forms the basis of special relativity and underpins the modern understanding of space, time, and energy. When we observe distant galaxies, we rely on the fact that photons emitted billions of years ago travelled at this constant speed to deliver accurate information about distance, velocity, and the state of the universe at emission. The implications of the speed limit extend to exotic phenomena, such as black holes. The event horizon of a black hole is defined by the speed of light. Any object crossing this boundary cannot escape, because it would need to travel faster than light to do so. The same principle applies across the universe. Local superluminal motion is impossible. Yet the stretching of space during cosmic expansion allows apparent recession velocities to exceed c. Observing these superluminal recessions, which occur in distant galaxies, does not contradict the speed limit, because the galaxies themselves are not moving through space faster than light. They are being carried by the expanding fabric of space. The speed of light also dictates the particle horizon, the maximum distance from which light has had time to reach an observer since the Big Bang. This horizon is not static. It grows as the universe ages, incorporating photons from increasingly distant regions as they finally arrive. While light travels locally at 299,792 kilometers per second, the expansion of space means that photons from beyond the Hubble radius are only now beginning to enter our observable universe. The speed of light shapes the timing and scale of what can be seen and measured. Even when considering the cosmic microwave background, the speed limit plays a central role. Photons emitted during recombination travelled at light speed, while space expanded beneath them. The CMB we observe today comes from regions that were only a few 100,000 light-years away at emission. Yet due to expansion, those regions are now over 46 billion light-years distant. The speed of light governs how long it took for the photons to arrive, while the expansion of space increases their co-moving distance, illustrating the interplay between light speed limits and cosmic growth. But galaxies recede faster than light? It seems impossible at first. We know that nothing can travel faster than light, yet the universe contains galaxies that are moving away from us at speeds greater than 299,792 kilometers per second. This is one of the most counterintuitive features of cosmology. Galaxies can recede faster than light, and yet relativity is not violated. The key is understanding the difference between motion through space and the expansion of space itself. Galaxies are not hurtling through space faster than light. They are embedded in the cosmic fabric, and it is the fabric of space itself that stretches. As space expands, the distance between distant galaxies increases, even if the galaxies themselves are nearly stationary with respect to their local space. This distinction is subtle but critical. In local terms, relativity holds. No mass can accelerate past light speed. On cosmic scales, however, the metric of space, the coordinates that define distances, changes over time, allowing the separation between distant galaxies to increase faster than light without violating any physical law. This leads to the concept of superluminal recession. Beyond a certain distance from any observer, galaxies recede at speeds exceeding light due to the expansion of space. The threshold, where the recession velocity equals the speed of light, defines the Hubble radius, sometimes called the Hubble sphere. Today, the Hubble radius is roughly 14 billion light-years. Galaxies within this radius have recession velocities slower than light. Light emitted from them eventually reaches us. Galaxies beyond this radius recede faster than light, meaning that if space were expanding uniformly at that distance, their emitted photons would initially be carried away from us, unable to approach until the expansion rate slows relative to the photon's path. The Hubble radius is not a hard boundary, but a dynamic concept. As the universe evolves, the Hubble constant changes and the Hubble radius grows. This allows light emitted by galaxies currently beyond the Hubble sphere to eventually reach us if the expansion rate slows sufficiently. In this way, the observable universe continues to grow over time, but there remain limits beyond which light will never reach us. This interplay between the expansion of space and the speed of light defines the cosmic landscape and shapes what is visible to us. Closely related to the Hubble sphere is the particle horizon. The particle horizon marks the maximum distance from which light could have travelled to us since the beginning of the universe. Unlike the Hubble sphere, which is tied to the current expansion rate, the particle horizon is determined by the integral of the expansion history of the universe. Photons emitted at the earliest moments of cosmic time, travelling through rapidly expanding space, define this horizon. The particle horizon sets the ultimate boundary for the observable universe, approximately 46.5 billion light-years away. Anything beyond that distance has not yet had time to send light to us, no matter how long the universe exists. Another critical concept is the event horizon. This is not a black hole horizon, but a cosmological one. The event horizon defines a limit beyond which events occurring now can never influence us in the future. Due to the accelerated expansion of the universe driven by dark energy, some galaxies are receding so rapidly that light emitted today will never reach us. Their present co-moving distance places them beyond the cosmological event horizon. In practical terms, these galaxies are visible today because of photons emitted in the past, but any new light emitted now will never traverse the expanding space to reach Earth. The event horizon represents a permanent boundary for future causal contact, a limit set by the combination of light speed and accelerating expansion. Superluminal recession also explains why the most distant galaxies we observe today were much closer when they emitted their light. A galaxy at a current co-moving distance of 46 billion light-years may have been only a few billion light-years away at the time of emission. Light emitted then moved at the speed of light relative to local space, but space itself stretched underneath it, carrying the galaxy farther away during the photon's journey. By the time the light reaches us, the galaxy resides far beyond the Hubble radius, yet the photon has made the journey through the expanding cosmic fabric. This is why the observable universe contains regions receding faster than light, yet light from them still arrives. The mathematics behind these horizons comes from the Friedmann-Lemaitre-Robertson-Walker metric. Distances are not fixed. They depend on the scale factor AT, which grows over time. The recession velocity of a galaxy is given by h of t times d, where h of t is the Hubble parameter at that epoch, and d is the proper distance. Beyond the Hubble radius, h of t times d exceeds c, giving superluminal recession. The expansion is embedded in the geometry of spacetime, so no physical law is broken. Light speed limits apply locally, but the metric of space changes globally. Dark energy plays a central role in shaping superluminal recession. As the universe accelerates, galaxies previously within reach can move beyond the event horizon. Observations of Type 1a supernovae and the cosmic microwave background confirm this acceleration. The scale factor now grows exponentially, meaning that even nearby galaxies will eventually recede faster than light, effectively disappearing from our future horizon. Light emitted now from these galaxies will never reach us, although photons emitted billions of years ago are already en route. Cosmic expansion also affects the energy of photons. As space stretches, the wavelength of light increases, a process known as cosmological redshift. Photons from galaxies receding faster than light are redshifted to extreme wavelengths, eventually into the radio or microwave range. This redshifting demonstrates how the universe's growth not only increases distances, but transforms the energy of light travelling through space. Observing these photons allows astronomers to trace the history of cosmic expansion and measure distances beyond the Hubble sphere. The distinction between motion through space and expansion of space becomes critical when considering structures like galaxy clusters. Within clusters, galaxies are gravitationally bound and local motions dominate. These galaxies do not recede superluminally from one another, despite the expansion of the universe. Between clusters, however, space stretches freely, and recession velocities can exceed light speed. Co-moving distance and redshift measurements capture both the local motions and the global expansion, separating bound systems from the unbound, expanding cosmos. Superluminal recession also introduces challenges in mapping the universe. Light from distant galaxies may initially move away due to expansion, then approach as the Hubble parameter evolves. This means that photons emitted beyond the Hubble radius at one moment can eventually reach us later, depending on the universe's expansion history. Cosmologists must carefully account for this when converting redshift into distances, using models that integrate the changing Hubble parameter over time. The universe is dynamic, and the geometry of space stretches the rules of motion across cosmic scales. The observable universe, as defined by the particle horizon, contains regions moving away faster than light, yet the light from those regions can still arrive if it was emitted early enough. The Hubble radius defines the boundary for current recession at light speed, while the event horizon sets the ultimate limit for future visibility. Light from galaxies between these horizons behaves in complex ways. It can move toward us, be slowed by expansion, or eventually become unreachable. The interplay of these horizons defines the cosmic architecture, revealing why the universe can appear simultaneously finite in what we can see, yet infinite in its potential extent. Cosmic expansion also shapes the timeline of visibility. Galaxies that emitted light billions of years ago may now be receding faster than light. Observing them requires that the light was emitted when the galaxy was within a slower expanding region of space. These photons arrive today, carrying information from an era when local motion and expansion allowed them to make progress. Photons emitted later from the same galaxies will never reach us if the recession velocity exceeds light speed, illustrating the precise timing and scale dependence of superluminal expansion. Even extreme redshift galaxies and quasars demonstrate this effect. Objects with redshifts above 10 emitted light when the universe was less than 500 million years old. Their present recession velocities exceed the speed of light. Observing these objects requires understanding the expansion history, the Hubble parameter over time, and the relationship between co-moving distance and particle horizon. The photons we detect were able to traverse the expanding space because they were emitted early enough before superluminal recession prevented progress. The Hubble sphere itself is a conceptual tool. It is the radius at which recession velocity equals light speed at a given epoch. Today, this is roughly 14 billion light-years. Photons emitted just inside the Hubble sphere will eventually reach us, while those emitted just outside may initially move away. As the Hubble parameter changes over time, the Hubble radius expands, and some photons initially receding faster than light can eventually enter the observable universe. This evolving boundary emphasizes that cosmic horizons are dynamic, not fixed. The interplay of particle horizon, event horizon, and Hubble sphere defines the observable cosmos. The particle horizon sets the maximum distance light has traveled since the Big Bang. The Hubble sphere marks the local recession velocity equal to c. The event horizon defines regions permanently beyond causal contact. These constructs, combined with superluminal recession, explain why the universe can appear larger than its age in light years, why distant galaxies recede faster than light, and why the cosmic microwave background can arrive despite its source being billions of light years away at emission. Superluminal recession also frames our understanding of future cosmic visibility. Galaxies currently within view will eventually cross the event horizon as expansion accelerates. Light emitted today by those galaxies will never reach us. This sets a dynamic limit on future astronomy. The observable universe will shrink in terms of new information, leaving only the photons emitted in the past. Observations of today's distant galaxies capture a universe that is continuously growing beyond our reach, even as light from past epochs continues to arrive. The dark energy twist. In 1998, the universe surprised the scientific world in a way that no one expected. Astronomers studying distant supernovae, stellar explosions so bright they can outshine entire galaxies for weeks, noticed something astonishing. They discovered that the universe's expansion wasn't slowing down under the pull of gravity, as everyone assumed. It was speeding up. The teams making this discovery were led by Saul Perlmutter, Brian Schmidt, and Adam Rees. They were measuring the brightness of Type 1a supernovae, which act as standard candles, because their intrinsic luminosity is known. By comparing the apparent brightness of these explosions to their expected luminosity, they could calculate distances with remarkable precision. Combining this information with measurements of redshift, the degree to which light stretches as the universe expands, they could map how the universe's expansion rate had changed over time. Initially, the expectation was simple. Galaxies and cosmic structures should be moving apart, but gravity should gradually slow this motion. The more mass the universe contains, the stronger this deceleration should be. Observations of nearby supernovae confirmed this expectation. But when the teams looked at supernovae billions of light years away, the results were shocking. Those distant explosions appeared dimmer than predicted. Dimmer means farther. Farther than expected given the known expansion rate. That implies that galaxies were moving away faster in the past than current models predicted. The universe wasn't slowing down, it was accelerating. The data left astronomers in disbelief. The acceleration could not be explained by known matter, dark or visible. It required a new component of the universe, something counteracting gravity, pushing space itself apart. This was the first clear evidence of dark energy. The supernova observations were precise, repeated and verified by independent teams. One group led by Saul Perlmutter at the Supernova Cosmology Project, and another led by Brian Schmidt and Adam Rees at the High Z Supernova Search Team, both arrived at the same unexpected conclusion. Cosmic expansion is accelerating. This acceleration rewrote our understanding of the cosmos. Previously, the universe was seen as a battle between expansion from the Big Bang and the gravitational pull of all matter. Scientists calculated whether the universe would eventually stop expanding and collapse, stabilize, or continue expanding slowly. The discovery of acceleration changed that framework completely. Now, the universe had an invisible force, a form of energy inherent to space itself that overwhelms gravitational attraction on large scales. The concept was initially met with skepticism. Acceleration defied intuition. How could empty space push galaxies apart faster than gravity can pull them together? To answer this, scientists revisited Einstein's equations of general relativity. Albert Einstein had introduced the cosmological constant, denoted by lambda, to allow for a static universe. He later called it his greatest blunder, when the universe was discovered to be expanding. But the 1998 findings gave new life to this concept. The cosmological constant, once discarded, could explain a uniform energy density in space causing acceleration. The supernova data fit naturally with this framework, linking observational results to fundamental physics. Type 1. A supernovae were crucial because of their reliability. These explosions result from white dwarf stars in binary systems reaching a critical mass, igniting in a uniform thermonuclear detonation. Their brightness is well understood, making them precise distance indicators. By measuring their redshift and apparent luminosity, astronomers could construct a cosmic expansion history. It was through these measurements that the accelerating expansion became undeniable. Distant supernova did not match the predicted brightness if the universe's expansion was slowing. Instead, the dimming revealed acceleration, indicating a force opposing gravity on cosmological scales. The discovery relied on both observation and careful statistical analysis. Each supernova is affected by local environments, dust, and intrinsic variations. The teams painstakingly accounted for these factors, comparing hundreds of explosions across different distances and directions. The consistency of results across independent datasets eliminated the possibility of observational error or selection bias. The conclusion was stark. The universe is not just expanding, it is expanding faster over time, and this acceleration dominates the dynamics of the cosmos. This discovery led to a new paradigm. Matter, both visible and dark, contributes only part of the universe's total energy density. To produce acceleration, a repulsive component is required. Dark energy emerged as the name for this mysterious substance. It is not matter in the conventional sense. It is not composed of particles we can detect directly. Instead, it is a property of space itself, producing negative pressure that drives expansion. Unlike gravity, which pulls matter together, dark energy pushes the fabric of space apart, causing the acceleration observed in distant galaxies. The implications were immediate and profound. The age of the universe had to be recalculated. Previous models based on decelerating expansion underestimated the time it would take to reach the observed distances of faraway galaxies. With acceleration, the universe is older than previously thought. Cosmologists use the supernova data in combination with the cosmic microwave background and large-scale structure measurements to refine the age of the universe to roughly 13.8 billion years. Acceleration changes the cosmic clock, stretching timelines and distances alike. The scale of acceleration is subtle but cumulative. Each galaxy feels an imperceptible push from dark energy locally, but over billions of light years, this cumulative effect becomes enormous. Over the course of cosmic history, the influence of dark energy has grown to dominate over matter, leading to an exponential increase in the scale of space. The discovery of acceleration revealed that the universe's future is not a slow, gradual expansion, but a trajectory toward ever faster growth, shaping the destiny of galaxies and the cosmic web. The observational techniques involved were groundbreaking. Advanced telescopes and detectors allowed teams to measure redshift with precision, even for faint supernovae billions of light-years away. Observatories such as the Cerro Tololo Inter-American Observatory and the Hubble Space Telescope provided critical imaging and spectroscopy. Photons travelling for billions of years were captured and analysed, revealing minute differences in brightness that indicated acceleration. These observations transformed cosmology from theoretical speculation into an empirical science of expansion dynamics. The discovery also triggered a re-examination of fundamental physics. Dark energy cannot be explained by conventional matter or known forces. It requires new physics, possibly tied to the vacuum energy predicted by quantum mechanics. The energy density of empty space, long assumed to be negligible, became central to understanding cosmic acceleration. The supernova data provided the first solid measurement of this energy component, showing that it accounts for roughly 68% of the total energy density of the universe. Ordinary matter, including stars, gas, and dark matter, contributes only about 32%, highlighting the dominance of dark energy in shaping the cosmos. The team's work set the stage for a wave of follow-up studies. Observations of baryon acoustic oscillations, the distribution of galaxies, and precision mapping of the cosmic microwave background confirmed that acceleration is a universal phenomenon, not a localized anomaly. The combined evidence from multiple independent probes established dark energy as the primary driver of cosmic expansion today. The 1998 supernova observations were the first window into this hidden energy, reshaping our understanding of the universe in a way that no discovery before or since has matched in impact. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, cementing their work as a cornerstone of modern cosmology. Their findings open new questions. What is dark energy? Why does it have the observed value? And how will it affect the universe in the distant future? The answer is not trivial. The acceleration observed requires that space itself has a repulsive property, one that is counterintuitive and unlike any force experienced in the laboratory. It challenges the very definition of energy and pressure in physics, linking cosmology with fundamental particle theory and general relativity. The 1998 discovery also changed the way cosmologists model the universe. Acceleration implies that the universe will expand faster and faster, potentially isolating galaxies from one another over immense timescales. Observing distant supernovae provides a snapshot of the universe before acceleration became dominant, allowing astronomers to map how the expansion rate evolved over billions of years. Each distant explosion encodes information about the balance between gravity and dark energy at its epoch, giving a historical record of the cosmic tug-of-war. Supernova observations revealed that acceleration is uniform in all directions. The most distant explosions show the same behavior whether observed in the northern or southern sky. This isotropy implies that dark energy is a property of space itself, evenly distributed throughout the cosmos. Unlike matter, which clumps under gravity, dark energy does not cluster. It fills all space, producing a smooth, persistent pressure that drives exponential expansion. This uniformity is critical for cosmological models, allowing predictions of future expansion and providing a foundation for connecting the early universe with its large-scale structure today. Dark energy, 68% of total cosmic energy density. The discovery of cosmic acceleration immediately pointed to a force dominating the universe: dark energy. Unlike matter or radiation, dark energy is invisible, pervasive, and counterintuitive. It does not cluster into galaxies or stars. It fills every corner of space uniformly. Observations indicate that it makes up roughly 68% of the universe's total energy density, outweighing matter and dark matter combined. On the largest scales, it governs how the cosmos evolves, driving galaxies apart with a relentless, unyielding push. Physicists often describe dark energy in terms of the cosmological constant, lambda, a concept introduced by Albert Einstein nearly a century ago. Initially, Einstein proposed lambda to allow a static universe, countering gravity's pull. After the discovery of cosmic expansion, he abandoned it, calling it his greatest blunder. But the 1998 supernova observations gave the cosmological constant a modern revival. In essence, lambda represents a fixed energy density of empty space, unchanging over time, that exerts negative pressure on the universe. It is uniform, isotropic, and constant, unlike matter, which dilutes as space expands. Negative pressure is a challenging concept because it defies everyday intuition. Pressure is usually thought of as a force pushing outward. In general relativity, however, pressure itself contributes to the gravitational field. Positive pressure strengthens gravitational attraction, while negative pressure produces repulsion. Dark energy's negative pressure outweighs the gravitational pull of matter and dark matter, resulting in accelerated expansion. Space does not merely expand at a steady rate. the scale factor grows faster and faster, producing an effect that can be mathematically described as exponential expansion. Observations from multiple sources confirm dark energy's dominance. Supernova surveys provide direct evidence, but other cosmological measurements corroborate the finding. The cosmic microwave background reveals the universe's geometry, indicating it is spatially flat. Baryon acoustic oscillations map the distribution of galaxies, showing the imprint of expansion over time. Weak gravitational lensing measures the growth of structure, sensitive to the competing effects of gravity and dark energy. These lines of evidence converge. A constant, pervasive energy component with negative pressure now controls the universe's expansion. The cosmological constant can be quantified. Using modern cosmological parameters, lambda corresponds to an energy density of about 6.91 times 10 to the power of minus 10 joules per cubic meter. It seems incredibly small compared to familiar energies, yet across billions of cubic light years, its cumulative effect dominates the dynamics of the universe. The subtlety of its magnitude is striking. Though nearly undetectable on local scales over cosmic distances, it determines the fate of galaxies, clusters, and the large-scale structure of space itself. Dark energy affects both the past and future of the universe. In the past, matter dominated and gravity slowed expansion. As the universe aged, the density of matter decreased due to cosmic expansion, while the energy density of lambda remained constant. At some point, roughly 5 billion years ago, dark energy overtook matter as the primary influence on cosmic dynamics. Since then, the expansion has been accelerating, shaping the universe into a vast, ever-stretching landscape where distant galaxies move away faster than light due to space itself expanding. The exponential growth driven by dark energy has profound consequences. Unlike expansion dominated by matter, which slows over time, a lambda-dominated universe accelerates indefinitely. The scale factor A of t increases exponentially, meaning that the separation between unbound galaxies grows faster with each passing epoch. Distant structures, once observable, may eventually recede beyond the event horizon, never to be seen again. The universe is heading toward a future where isolated galaxies and clusters will drift beyond contact, separated by ever-expanding space. The cosmological constant is one model of dark energy, but the term encompasses broader possibilities. Alternatives include dynamic scalar fields, sometimes called quintessence, which can change in density and pressure over time. Unlike lambda, these fields may evolve, vary across regions, or decay in the future, potentially altering the ultimate fate of cosmic expansion. Observational programs are actively testing these possibilities, measuring the equation of state parameter dBW, which relates pressure to energy density. A perfect cosmological constant has WW equals -1. Deviations would imply evolving dark energy. Dark energy also affects cosmic structure formation. Negative pressure suppresses the growth of new gravitationally bound structures. Clusters of galaxies and filaments that form under the influence of matter may eventually become isolated as dark energy accelerates expansion between them. The cosmic web freezes in place on the largest scales. Gravitational collapse is countered by repulsive expansion, leaving structures that can only grow locally. Beyond certain distances, the universe's large-scale network effectively stops evolving. The presence of dark energy links directly to fundamental physics. Quantum mechanics predicts a vacuum energy, a zero-point energy inherent to empty space. Calculations, however, overestimate its magnitude by many orders of magnitude compared to observations, producing the cosmological constant problem. Why the observed lambda is so small, yet non-zero, remains one of the deepest mysteries in physics. Supernova measurements provide the first empirical handle on this quantity. but theoretical understanding lags behind observational precision. The tiny, persistent energy density of space, revealed by distant explosions billions of light years away, challenges our understanding of reality itself. Exponential expansion caused by dark energy has implications for the light we observe. Photons travelling through a lambda-dominated universe are redshifted more strongly over time. The wavelengths stretch as space grows, lowering their energy and moving visible light into infrared, microwave, or radio frequencies. This cosmic stretching explains why the most distant galaxies appear faint and extremely redshifted. Light emitted billions of years ago from a galaxy that today is tens of billions of light years away has travelled a universe that is expanding faster and faster, carrying its energy across the accelerating cosmic fabric. Dark energy's dominance is not just a theoretical concern, it is evident in observations of the Hubble parameter over time. Measurements of local supernovae, galaxy clusters, and large-scale structures all reveal that expansion has transitioned from deceleration to acceleration. The transition marks the point when the negative pressure of dark energy outweighed the gravitational attraction of matter. This shift changes not only distances, but also the dynamics of motion across space. Galaxies once bound to expand slowly are now carried apart faster than light due to the increasing influence of lambda. The cosmological constant also connects to the future of the universe in precise terms. In a lambda-dominated cosmos, the scale factor evolves as O of t approximately equals e to the power of ht, where h is the Hubble parameter associated with lambda. This mathematical form describes exponential growth, meaning that over each unit of cosmic time, distances increase by a fixed factor. Unlike matter-dominated expansion, which slows, or radiation-dominated expansion, which decelerates rapidly, a lambda-dominated universe expands faster and faster, a process that continues indefinitely if lambda remains constant. Observational cosmology continues to refine the properties of dark energy. Projects like the Dark Energy Survey, Euclid, and the Vera Rubin Observatory aim to map the distribution of galaxies and supernova across the sky, measuring both the rate of expansion and the growth of structure. These surveys test whether dark energy behaves as a true cosmological constant or if it evolves. Precise measurements of W, the equation of state parameter, will reveal whether negative pressure is truly constant or changing over time. Early results are consistent with dW approximately equals -1, supporting the lambda interpretation, but uncertainties leave room for surprises. The uniformity of dark energy also defines the geometry of space. Observations show that the universe is spatially flat on the larger scales, consistent with lambda dominating the cosmic energy budget. Positive or negative curvature would influence expansion, but the near-perfect flatness observed in the cosmic microwave background and large-scale structure is explained naturally by a universe in which dark energy contributes roughly 2/3 of total energy density. The cosmological constant balances the gravitational pull of a matter, producing a geometry that remains flat as space stretches ever wider. The travel scenarios. Imagine setting off on the greatest journey possible, not just to the next city, not just to the moon, but to the very edge of what the universe lets us see. The distance is almost beyond comprehension. The observable universe stretches roughly 46.5 billion light years in every direction, and that's only what we can see. Beyond that, space goes on, but we have no information yet. The question we explore now is, if we could travel, how long would it take to reach the edge? How does speed affect time? And how does the universe's own expansion make even the fastest journey impossible? We'll break this down into a series of travel scenarios, each faster than the last, to understand both the scale and the physics involved. Scenario A, walking across the cosmos, 5 kilometers per hour. Let's start slow at the pace of a human walking, about 5 kilometers per hour. For perspective, that's roughly the speed of a casual stroll through a park. At this speed, distances that seem enormous in everyday life are barely noticed. A city may take hours to cross, a country days. But what happens when we scale that up to interstellar distances? Consider the Andromeda Galaxy, the nearest spiral galaxy to the Milky Way, lying some 2.5 million light-years away. A light-year, the distance light travels in 1 year, is roughly 9.46 trillion kilometers, which makes Andromeda about 23.65 quintillion kilometers from Earth. Convert those hours into years, and the journey stretches to about 540 trillion years. The universe itself is only 13.8 billion years old. Walking to our nearest galactic neighbour at a human pace would take almost 40,000 times the current age of the universe. Turning closer to home, the Milky Way stretches across roughly 100,000 light-years in diameter. At the same leisurely pace of 5 kilometers per hour, crossing our own galaxy would require travelling more than 946 quadrillion kilometers. That distance would take approximately 189 quadrillion hours to cover. Converting to years, the journey spans roughly 21.6 trillion years, far longer than the lifetime of the Milky Way itself. Even at a human walking pace, distances inside our own galaxy are so vast that human lifespans, civilizations, and even the existence of stars seem like a blink. Walking is, of course, absurdly slow on cosmic scales, but it gives a visceral sense of scale. The universe is not just large, it is incomprehensibly large. Scenario B, commercial jet, 900 kilometers per hour. Next, let's speed up to a commercial jet. A typical passenger plane travels about 900 kilometers per hour, roughly 180 times faster than walking. For humanity, that's the fastest we normally experience on Earth. It takes hours to cross continents, but in space, distances dwarf this speed. At this pace, the journey to the Andromeda Galaxy would still be unimaginably long. Covering the roughly 23.65 quintillion kilometers to our nearest spiral neighbor would take about 26 quadrillion 300 trillion hours. Convert those hours into years, and the trip stretches to around 3 trillion years. Even at jet speed, the journey is more than 200 times longer than the current age of the universe, a span so vast it dwarfs any measure of human history. Turning inward to our own Milky Way, crossing its 100,000 light-year diameter at 900 kilometers per hour would still require travelling 946 quadrillion kilometers. That distance would take more than 1 quadrillion 50 trillion hours to cover, which translates to approximately 120 billion years. Even at the speed of a jet, what feels fast on Earth becomes glacial when scaled to the size of our galaxy. These numbers make it clear, speed alone, measured in human terms, is utterly insufficient to traverse the cosmic distances that surround us. Even at jet speed, it takes 120 billion years to walk across the galaxy. Commercial planes make our planet feel small, but in cosmic terms, they are glacially slow. Scenario C, Voyager 1 speed, approximately 17 kilometers per second. Now we accelerate dramatically. Voyager 1, humanity's farthest travelling spacecraft, moves at roughly 17 kilometers per second, or 61,200 kilometers per hour. That is over 60 times the speed of sound. At this speed, interstellar travel becomes a measurable, but still astronomical task. At this incredible velocity, distances that once took trillions of years to cross begin to shrink, but they remain vast beyond comprehension. The journey to the Andromeda Galaxy, our nearest spiral neighbour, would still require travelling more than 23.65 quintillion kilometres. At Voyager 1 speed, That distance translates to roughly 386 trillion hours. Convert those hours into years, and the trip would take about 44 billion years. That is still more than 3 times the current age of the universe, a span that dwarfs everything humanity has ever known. Crossing the Milky Way, which stretches across roughly 100,000 light-years, would take nearly 155 trillion hours at this speed. In years, that comes out to about 1.77 billion years. Even at Voyager 1 speed, crossing our own galaxy requires enough time for entire civilizations, empires, and stars to rise and fall multiple times. Voyager 1, the fastest object ever built by humanity, illustrates just how immense the universe truly is. Even if we take this speed to its absolute cosmic extreme and consider the edge of the observable universe, some 46.5 billion light-years away, the numbers become staggering. That distance converts to roughly 440 sextillion kilometers. Traveling at 17 kilometers per second, it would take about 7.2 quintillion hours to reach the edge. When translated into years, the journey spans around 820 trillion years. Even at the speed of Voyager 1, reaching the cosmic horizon is impossible within any timescale meaningful to the universe as we know it. By the time a spacecraft could arrive, the universe itself would have evolved into something almost unrecognizable, with galaxies moving far beyond their original positions and stars long extinguished. Scenario D, 10% of the speed of light, 0.1 c. Now we enter the realm of relativistic travel. Let's imagine a spacecraft moving at 10% of light speed, or 0.1 c, roughly 30,000 kilometers per second. Suddenly, time dilation starts to matter, and distances shrink in the spacecraft's frame. Traveling to the Andromeda Galaxy at 10% of the speed of light, a distance of 2.5 million light-years, would take about 25 million years, ignoring the effects of time dilation. Even at this incredible speed, the journey still spans tens of millions of years, but it begins to fall within a scale that is at least imaginable when compared to the lifetimes of civilizations. Crossing the Milky Way, which stretches roughly 100,000 light-years across, would take about 1 million years at the same speed. Now we are talking about trips that could be conceivable in a science fiction sense. 1 million years for an interstellar voyage, 25 million years for the nearest galaxy. Time dilation becomes noticeable. The astronauts aboard a ship moving at 0.1 c would experience slightly less time than an observer on Earth, although at this speed, the effect is small. Traveling to the observable edge of the universe, 46.5 billion light-years, ignoring expansion for a moment, that's 465 billion years. Even at a tenth of the speed of light, the timescale is immense, hundreds of times the current universe's age. Scenario E, 99.999% of the speed of light, 0.99999 c. Here we enter extreme relativistic territory. At 99.999% of c, relativistic effects dominate. Time dilation becomes extreme. From the perspective of travelers, their clocks run far slower than those on Earth. This is described by the Lorentz factor. Gamma equals 1 over the square root of 1 minus v squared over c squared. At 0.99999 c, gamma is approximately 224. What does this mean? A journey that takes billions of years from Earth's frame can feel like millions or thousands of years to the traveller. For example, reaching the observable universe's edge, 46.5 billion light-years, at 0.99999 c, Earth frame time, 46.5 billion light-years divided by 0.99999 c is approximately 46.5 billion years. Traveller frame time, 46.5 billion divided by 224, is approximately 207 million years. Suddenly, the scale becomes almost humanly imaginable on cosmic timescales. However, even at this extreme speed, relativistic mass increases. The energy required to accelerate a spacecraft approaches infinity as it nears C. Fuel requirements become impossible with known technology, and collisions with even sparse interstellar gas could have catastrophic effects. Scenario F, the speed of light, hypothetical photon. Finally, the ultimate speed, light itself. Photons travel at 299,792 kilometers per second, the ultimate cosmic speed limit. At first glance, one might think photons could reach the edge of the observable universe in 46.5 billion years. But the universe expands while the photon travels. Space stretches underneath it. The photon's progress relative to the edge is slowed by cosmic expansion. Even for light, observable universe edge recedes faster than light beyond certain distances. Photons emitted now from galaxies beyond the Hubble radius will never reach us. Expansion stretches wavelengths, cosmological redshift, lowering energy. Light from the farthest regions is already microwave, not visible. No matter how fast we travel, even hypothetically at light speed, the expanding fabric of space sets a moving target. The edge of the observable universe is not a fixed point. It recedes continuously, faster than any traveller can approach. At this point, the patterns are clear. Ordinary speeds, walking, jets, Voyager 1 take trillions of years to reach even nearby galaxies. Relativistic speeds compress time via time dilation, but fuel, energy, and collisions present barriers. The expanding universe creates a horizon. Even light cannot reach regions beyond the Hubble radius today. The Event Horizon Problem. Imagine standing on a quiet shore at night, looking out across a dark ocean. The horizon marks the limit of what you can see, but if the ocean itself were rising and stretching, that horizon would not stay still. It would shift, drift, and pull away from you. Now replace the ocean with space itself. Replace the water with galaxies. Replace the shoreline with Earth. This is the strange reality of the cosmic event horizon. When we look into the night sky, we are looking into the past. Light from distant galaxies has been traveling for billions of years before reaching us. Because the universe is about 13.8 billion years old, you might think we can see out to 13.8 billion light years. But space has been expanding the entire time that light was traveling. As a result, the most distant galaxies we can observe today are not 13 billion light years away. They are now about 46.5 billion light years away. That defines the observable universe. But the observable universe is not the same thing as the reachable universe. That distinction is where the event horizon problem begins. The cosmic event horizon marks a boundary beyond which events happening today will never be seen by us, no matter how long we wait. It is not about what we can see from the past. It is about what we can ever see in the future. Right now, there are galaxies whose light is reaching us for the last time. The light we receive from them today left billions of years ago. But the light they emit now, at this moment, will never reach Earth. Space between us and those galaxies is expanding too quickly. The gap grows faster than light can cross it. The key number is roughly 16 billion light years. That is the approximate radius of the reachable universe. Any galaxy currently farther than about 16 billion light years away is permanently unreachable in terms of future communication or travel, even if we could move at the speed of light. This sounds impossible at first. Nothing can move faster than light. So how can galaxies move away from us faster than light? The answer is subtle, but crucial. They are not moving through space faster than light. Space itself is expanding. The fabric of the universe stretches. If two galaxies are far enough apart, the stretching between them increases their separation faster than light can bridge it. This does not break the laws of relativity, because relativity limits motion through space, not the expansion of space itself. To understand the event horizon problem, we need to separate two ideas: observable and reachable. The observable universe includes everything whose past light has had enough time to reach us since the beginning of cosmic time. That sphere extends roughly 46.5 billion light-years in every direction. That is what we can see today. The reachable universe is smaller. It includes only the region from which light emitted today could eventually reach us in the infinite future. That boundary lies much closer, at about 16 billion light-years. Between 16 and 46 billion light-years lies a vast region that we can observe, but can never influence or reach. We see those galaxies as they were billions of years ago. But if we tried to send a signal today, even at light speed, it would never arrive. The expansion of space would stretch the distance faster than our signal could close it. That is the event horizon problem. The universe contains regions that are visible but forever disconnected. Over time, this effect grows stronger. The expansion of the universe is accelerating due to dark energy. As space expands faster and faster, more galaxies cross beyond the event horizon. Once they pass that boundary, they are gone from future contact forever. Their light fades, their signals weaken. Eventually, even their ancient light stops arriving. In the distant future, observers in our galaxy will see far fewer galaxies than we do today. Billions of years from now, most galaxies will have slipped beyond the event horizon. The night sky will grow darker, emptier. Only the galaxies gravitationally bound to us will remain visible. Everything else will disappear beyond an unreachable boundary created by cosmic acceleration. This leads to a strange thought. The universe we observe today is not the same universe observers will see in the far future. Our cosmic era is special. We live at a time when distant galaxies are still visible. Trillions of years from now, observers may see only their local group of galaxies and assume that is the entire universe. They would have no evidence of the larger cosmos. The expansion would have erased it from view. The event horizon problem shows that the universe is not just vast. It is dynamically separating itself into isolated islands. Even if we imagine building a spacecraft capable of traveling at nearly the speed of light, the reachable limit remains. You cannot outrun the expansion of space beyond that boundary. If you aim toward a galaxy already past the event horizon, you will never arrive. The space between you and the galaxy grows too quickly. It is like running up a downward-moving escalator that moves faster than you can run. No matter how hard you try, you never gain ground. The reachable radius of about 16 billion light-years depends on the current rate of expansion and the influence of dark energy. As dark energy drives accelerated expansion, the event horizon stabilizes at a certain scale. It does not grow without limit. Instead, it creates a permanent barrier. This horizon is not a physical wall. There is no glowing edge in space. It is a limit defined by the geometry of expanding spacetime. It exists because of the relationship between the speed of light and the accelerating expansion of the universe. The concept challenges our intuition because we are used to thinking of space as static. On Earth, distances do not grow on their own. In the cosmos, distances do grow. The further apart two galaxies are, the faster they recede from each other. At sufficiently large distances, that recession exceeds light speed. This does not mean those galaxies are breaking physics. Locally, nothing outruns light. But globally, the metric expansion of space allows distances to increase without limit. Now imagine a galaxy currently 15 billion light-years away. That galaxy is just within the reachable limit. A light signal sent today would eventually reach it, given infinite time. But if the galaxy is 17 billion light-years away, it lies beyond the cosmic event horizon. No signal sent today will ever arrive. The difference between 15 and 17 billion light-years is small compared to the full observable radius of 46 billion light-years. Yet that small difference determines whether cosmic contact is possible. This is not science fiction. It is the direct consequence of measured cosmic acceleration. The event horizon problem becomes even more profound when we consider the early universe and cosmic inflation. Shortly after the Big Bang, the universe underwent a period of extremely rapid expansion known as cosmic inflation. This idea was proposed in 1980 by physicist Alan Guth. Inflation suggests that between roughly 10 to the negative 36 seconds and 10 to the negative 32 seconds after the Big Bang, the universe expanded exponentially. Those numbers are almost impossible to grasp. 10 to the negative 36 seconds is a decimal point, followed by 35 zeros, and then a 1. That is a fraction of a fraction of a fraction of a second, beyond ordinary imagination. Yet within that tiny interval, the universe expanded by an enormous factor. Before inflation, the observable universe may have been smaller than a proton. During inflation, it expanded faster than the speed of light, doubling in size again and again in an exponential burst. In a tiny fraction of a second, it grew from subatomic scale to macroscopic size. This rapid expansion helps explain several puzzles. It accounts for the remarkable uniformity of the cosmic microwave background. Regions of space that are now far apart were once close enough to exchange energy and reach the same temperature. Inflation stretched them apart after they became uniform. Inflation also explains why the universe appears spatially flat. Exponential expansion smooths out curvature, just as inflating a balloon makes its surface appear flatter over small regions. But inflation has a deeper implication. If inflation occurred once, it may have occurred in many regions. Some models suggest that inflation never completely ended. Instead, it continues in distant regions of space, creating a vast multiverse of expanding domains. Even without invoking a multiverse, inflation implies that the universe beyond our observable patch is far larger than we can see. The observable universe is only a small bubble within a much greater whole. That greater whole may be finite but enormous, or it may be infinite. If the universe is infinite, then there are regions beyond our horizon extending without end. Even if it is finite, it could be so large that our observable region is insignificant in comparison. Combine inflation with the cosmic event horizon, and the picture becomes astonishing. Not only is the universe larger than what we observe, but even within what we observe, large regions are forever unreachable. We are inside a visible sphere 46 billion light-years in radius, but only a smaller sphere of about 16 billion light-years is reachable in principle. Beyond that lies a region we can see only in ancient light, and beyond the observable limit lies an even greater expanse we cannot see at all. The structure of reality is layered. There is the reachable universe. Beyond that is the observable universe. Beyond that is the unobservable universe shaped by inflation. Each boundary is defined not by walls, but by time, light, and expansion. The cosmic event horizon reveals that the universe is not simply large, it is partitioned by the speed of light and by the accelerating growth of space. Inflation suggests that what we see is only a tiny part of an unimaginably vast whole. Even if we mastered near-light speed travel, we would remain confined to a shrinking island of reachable space. And beyond our observational horizon, reality may stretch endlessly, far beyond the limits imposed by cosmic acceleration. The event horizon problem forces us to confront a humbling truth. The universe is structured in such a way that most of it is permanently beyond our reach. Not just difficult to visit, not just hard to see. Fundamentally disconnected by the laws of physics and the expansion of space itself. So how long would it take to reach the edge of the observable universe? The direct answer is simple. You cannot reach it. Not at light speed, not ever. The reason is subtle, but absolute. The edge of the observable universe is not a physical wall waiting somewhere in space. It is not a boundary you can travel toward and eventually touch. It is a limit defined by light and time. It marks the farthest distance from which light has had enough time to reach us since the beginning of the universe. If you set off today, even travelling at the speed of light, you would be moving through expanding space. And space itself is stretching. The farther you go, the faster distant regions recede. Because of dark energy, that expansion is accelerating. The separation between you and the most distant galaxies increases faster than you can close the gap. In terms of coordinate time, measured by observers at rest in the cosmic co-moving frame, the journey would require tens of billions of years just to approach the present observable boundary. But during that time, the boundary itself moves farther away. It is not fixed. It grows. From your perspective, travelling at near light speed, proper time would pass more slowly due to relativity. Your onboard clock might measure far less time than billions of years. But even in your own frame, the expanding geometry of space prevents you from ever overtaking the horizon. The observable universe is larger than the reachable universe. The reachable radius is smaller because cosmic expansion outpaces any possible motion. The edge is not a destination. It is a limit created by space-time itself.